All right, let's move on to section 2.2. Here, we're actually going to introduce the concept of probability. In the previous section, 2.1, we just talked about how to count up the number of ways something can occur. We use that in probability because the probability of an event occurring is the number of ways that the event can occur divided by the total number of possible outcomes. Okay, so let's get into it. Just the basic notion of probability is going to include the concept of a sample space, right? So first of all, a probability experiment is any process that can be repeated in which the results are uncertain. The sample space of a probability experiment is the collection of all possible outcomes of the experiment. And we'll typically use the letter S to denote the sample space. So for example, the sample space for flipping a coin would be S equals heads or tails. Okay, and that's the sample space. Let me try that again. That's my lame attempt to make a curly brace. These are supposed to be curly braces. But yeah, heads, tails, that's our sample space. We'll usually use capital letters such as A and B and E and F and things like that to denote a particular outcome or event. And finally, probability, right, is a measure of the likelihood of a random phenomenon or chance behavior. If all outcomes in a sample space are equally likely to occur, then the probability that an event E occurs is, as I've said, the number of ways that E can occur divided by the total number of possible outcomes, the total number of events in the sample space. We'll use a capital P to denote probability, just like you see here. Okay, so P of A means the probability that event A occurs. Okay, for example, if H is the event that you get heads when flipping a coin, then P of H would be 1/2, because there's one way to flip heads when you flip a coin, right? There's only two sides of the coin. So, and one of them is heads, so the probability of flipping heads is going to be 1 out of 2. Two possible outcomes, heads or tails, one of them is heads. Here's another example, maybe slightly better example. If E is the event that you roll a 3 or a 4 when rolling a standard fair 6-sided die, then the probability that E occurs is going to be 2 out of 6, because there are two ways for E to occur. You could roll a 3 or you could roll a 4. And there are 6 possible outcomes when you're rolling a die, so probability of E would be 2 out of 6. This reduces to 1/3, and so that's what we would write as our final answer. You could also give a decimal approximation for this and say that this is approximately 0.333, or however many decimal places you're asked to round to. This one would be 0.5, right? Probability of heads is 50%, so 0.5. Okay. Note that since the probability of E is the number of ways that E can occur divided by the number of possible outcomes, counting techniques are going to come into play. This first example doesn't really use any of the combinations and permutations and those kinds of counting techniques, but we might occasionally see probabilities where we have to use those counting techniques. So let's just look at a few examples of this basic notion of probability. This first one says, a bag contains 7 blue marbles, 5 red marbles, and 8 green marbles. You reach into the bag without looking. Part A asks, what is the probability you draw a blue marble? When we're writing out our work, I would like for you to write out the full probability statement. Don't just give me your answer, but say probability of, I'll use the letter B for blue, right? Or you could write out the word blue. You could say probability of blue or something like this. But I'm just going to use probability of B for blue. So probability of drawing a blue marble. Well, there were 7 blue marbles in the bag, so there are 7 ways that we could draw a blue marble. And how many marbles in the bag in total? Well, 7 plus 5 is 12, and then plus 8 more would be 20. So there are 20 marbles in the bag in total. 7 of them are blue. So the probability of drawing a blue marble is 7 out of 20. If you want to change that into a decimal, you can use the Desmos calculator or whatever other calculator you're familiar with, and this is exactly equal to 0.35. So there's a 35% chance of drawing a blue marble. By the way, Desmos will also reduce fractions for you. So if you had a fraction that needed to be reduced and you don't remember how to do that, just use the Desmos calculator. Okay, so part B says, what's the probability you draw a red marble? Well, this is going to be probability of R for red. Again, there were 20 marbles in the bag, and 5 of them were red. So the probability of drawing a red marble is 5 out of 20. We can reduce that by 5, right? This is the same as 1/4. That would be our final answer. Or as a decimal, you could call it 0.25. So there's a 35% chance of drawing a blue marble and a 25% chance of drawing a red marble. Moving on. Here's an example, I think, where we will use some counting techniques. Number 2 says, in California's Fantasy 5 lottery, players choose 5 unique numbers from 1 to 39. Lottery officials then choose 5 numbers at random from a raffle drum. If all 5 of a player's chosen numbers match the 5 numbers chosen by the lottery officials, regardless of order, the player wins the jackpot. Apparently, the largest jackpot ever won in this game was $729,000. So I don't know if that's still true, but it was true at one point. Okay, part A asks us, what's the probability that a player wins the Fantasy 5 jackpot? So, probability that you win. Well, let's see. You only get one guess, right? And there's only one right answer. So there's only going to be one possibility, one way to win the game. So that part's easy, right? We know the numerator is going to be 1. The harder part is figuring out what the denominator would be. In other words, figuring out how many possible combinations there are, how many possible combinations of numbers you could choose. And I think I'm kind of giving away the answer to the counting technique that we would use here, but let's think it through, right? So to decide how many different groups of numbers that we could choose, we need to use a counting technique. So we should ask ourselves, first of all, is repetition allowed here? And I think the answer is no, because the numbers have to be unique. Okay, so we're not going to choose 1, 1, 1, 1, 1, right? It has to be 5 different numbers, 5 unique numbers. Okay, so we're not going to be using exponents. It's either permutation or a combination. So to decide which of those, then we ask ourselves, does the order matter? And it looks like in this game, it doesn't, right? We're told regardless of order, right? If you get the right numbers, it doesn't matter if they're in the right order or not. And that makes this a combination problem. Okay, so this is a combination. We're picking between numbers from 1 to 39, so there are 39 possibilities, and we need to choose 5 of them to play the game. So this is 1 over 39, choose 5. And you could punch this into the Desmos calculator to figure out how much this is. Maybe I'll just type in 39, choose 5. So I'm going to do 39 NCR 39, choose 5. Okay. Oh, that's not as many as I thought. That comes out to 575,757. What an interesting number. 39, choose 5. So to see what that is as a decimal, let's do 1 over 575, 757. Okay, so this comes out to 1.7368438 4 times 10 to the negative 6. So once again, Desmos is giving us an answer in scientific notation, just like it was doing sometimes in the previous section. Notice that this time the exponent is a negative number, which means instead of moving this decimal to the right 6 times, we're going to move the decimal to the left 6 times. So if I move the decimal 1 time to the left, then it ends up right there. But I've got to move it 5 more times, which means I'm going to have 5 zeros and then the rest of these digits. Okay, so this is the answer in scientific notation. In standard notation, it would be 0 point, and then I've got to have 1, 2, 3, 4, 5 zeros, and then a 1, 7, 3, 6, 8, 4, or whatever. We should just round this. I'm sure that Desmos was rounding already, so I'll say that this is approximately, right, that number. So this is our exact answer. And this is the approximation as a decimal. Your chances of winning are pretty slim. It looks like they're pretty slim, right? But things could be worse. Part B asks, what would the probability of winning be if the numbers had to be chosen in the correct order? So if the order did matter, then we would use a permutation, right? We would say the probability that you win that game is 1 over 39 permute 5. And this is going to be way worse. Let's see. So 39 permute 5 is 69 million. 69,090,840. So if you have to get the numbers in the right order, right, your chances of winning are even worse. They're tiny. So let's see. This would be 1 over 69,090,840. That comes out to 1.447. Let's just round. We'll say it's approximately 1.447 times 10 to the negative 8. So we have to move the decimal 8 times to the left. I move it once, okay, but then I have to move it 7 more times. So I'm going to have 7 zeros. So this is going to be 0.1, 2, 3, 4, 5, 6, 7 zeros, and then a 1447. So it's a number that's so small, I think we can't even really fathom it. But it's like very unlikely that you would win that game. Okay, so that's the lottery. Some people like playing the lottery, though. You know, if you set a limit for yourself, it's probably okay, but gambling can get you into some real problems. Okay, speaking of gambling, we're going to see a lot of kind of gambling examples as we go through probability, and that's because probability was actually invented in order to help gamblers, basically. So very common examples include cards, and I used to think that, you know, everyone kind of had an understanding of what a deck of cards looks like, but I've learned through my years of teaching that not everyone is familiar with cards. And so here's a picture of what a standard deck of cards looks like. A standard deck of cards is going to have 52 cards in it, and these are the cards that are in the deck. So you'll have some clubs, diamonds, hearts, and spades. There are 13 of each. These are called suits. So you have 4 suits, and then each of those 4 suits has 13 ranks. Okay, so these are called ranks. The ranks go from ace, which is the same thing as 1, and then 2 through 10, and then we have jack, queen, and king. Diamonds and hearts are obviously red cards. Clubs and spades are obviously black cards. Let's answer some probability questions. So it says you shuffle the deck and draw a card. Determine the probability that the card is red. Probability of red. Well, we would need to count up the number of red cards. There are 13 diamonds and 13 hearts, and so that makes 26 red cards in total, okay? So probability of drawing a red card is 26 out of the 52 cards in the deck. That reduces to 1/2, or 50%. Some of you may have looked at this and said, well, there's a 50% chance you draw a red card because half the cards in the deck are red. And if you were thinking that, then that's good. That's just another way to think about doing the problem. We ended up at the same place, right? So that's good if you were thinking along those lines. Okay, what's the probability that we draw a spade? Probability of drawing a spade. Well, there are 13 spades, right? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 spades. The probability of drawing a spade then would be 13 out of the number of cards in the deck, 52. And that reduces to 1/4. Which again, some of you might have looked at the deck and you might have said, well, 1/4 of the cards are spades, so the probability of drawing a spade is 1/4, and you would be correct about that, right? That's the same as 25%. Okay, part C asks, what's the probability that the card is a 5? So probability that the card is a 5. Well, there are 4 5s in the deck, right? 1, 2, 3, 4. So that would be 4 out of 52. 4 out of 52 reduces to 1/13. I can't do the decimal part in my head, though, so let me type it into my calculator. So this is approximately, we'll round this to 4 decimal places. So to 4 decimal places, this is approximately 0.0769. Okay. By the way, as I'm going through these, you should kind of pause and try out the number or try out the problem before I give you my answer. But I'm just going to kind of fly through them. But yeah, you're going to get the most out of the lecture, I think, if you kind of participate, right, and try the problems out before I give you my answer. Part D asks, what's the probability that we draw a card and the number is and the card is a number that's more than 7? So in order for it to be a number, I think the face cards are not allowed here. So we won't count those, but it needs to be a number more than 7. That would be 7, 8, 9, or 10. But we're not going to say that the answer is 4 out of 52 because there aren't just 4 of these kinds of cards. There are actually 16 of them, right? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 16 cards that are more than 7. So probability that it's more than 7 is going to be 16 out of 52. I know that number reduces because both of those numbers are even. So I'm just typing it into the Desmos calculator to do that for me. I'm too lazy. This is 4/13, or approximately 0.3077 if we round to 4 decimal places. Okay, King of Diamonds. Let me erase all these black dots that I've put on the on the cards. Okay, King of Diamonds. What's the probability we draw the King of Diamonds? Well, there are 4 kings in the deck, but only one of them is the King of Diamonds. That's that guy right there. So we would say probability that it's the King of Diamonds is 1 out of 52, and that does not reduce. Okay. 1 out of 52 is approximately 0.0192. And then finally, part F asks, what's the probability that the card is a face card? Probability that you draw a face card. These are the face cards. Jacks, kings, and queens are face cards because they have faces on them, so they're called face cards. It looks like there are 12 of those. So probability you draw a face card is 12 out of 52. Which reduces to 3/13, which is approximately 0.2308. Okay, so that's how we would deal with cards if we had any probability questions about cards. We also will encounter sometimes some probability questions about dice. So let's practice with that. Part number 4 here says a pair of fair dice is rolled, and part A asks us to determine the sample space. Remember, the sample space from page 1 of the notes is just, it's all of the possible outcomes. So if you roll a pair of fair dice, well, let's write out our sample space. We'll say S equals, I'm going to list each outcome as an ordered pair, where the first coordinate of the ordered pair is what you rolled on the first die, and the second coordinate of the ordered pair is what you rolled on the second die. So it's possible, one possibility is that you roll a 1 on the first die and a 1 on the second die, right? So that's one possible outcome. Another possible outcome would be rolling a 1 on the first die and then a 2 on the second die. It's also possible that you roll a 1 and a 3. And I think you see where this is going, right? So those are all of the possible outcomes if you roll a 1 on the first die. But of course, it's also possible that you might roll a 2 on the first die. You could roll a 2 and a 1, or a 2 and a 2, or a 2 and a 3, and so forth. And now I think you probably see where this pattern is heading, right? We'll have all of these possibilities. So I will write these out and then skip forward. Okay, so here are all of the possible outcomes. You should write these down because anytime you're dealing with dice, this would be a useful tool to come back to and look at. So if you haven't finished writing them down, go ahead and pause the video and write these out. But this is the sample space. Notice that there are 36 possibilities here, and that makes sense because there are 6 possibilities for the first die and 6 possibilities for the second die. So if we're trying to count up the number of possibilities, we would use the multiplication rule and say, well, it's 6 times 6, right? 36. Okay, part B asks, compute the probability of rolling a 3 first and then a 4. So probability that we roll a 3 first and then a 4. Well, there was only one of those in the sample space, right? So it would have to be 1 out of 36. Or as a decimal, that's about 0.0278 if we round to 4 decimal places. Part C asks us to compute the probability that the sum of the dice is 7. Well, if we roll a 3 and a 4, that'll give us a 7. That's one way to get it. But we would also get a 7 by rolling a 4 and a 3, or by rolling a 2 and a 5, or a 1 and a 6. In fact, everything along this kind of off diagonal here will sum up to be a 7. I don't think anything else will. If we go to the row above that, right, if we go to this row right here, those all add up to be 6. which is not what we want. And if we go to this row here, I think, or this diagonal, I should say, this diagonal, those all add up to be 8, which is also not what we want. So I think what we want are these ones, okay? So we'll say probability that the sum is 7. Well, there were 1, 2, 3, 4, 5, 6 of those out of 36 possibilities. And that reduces to 1/6, which is approximately 0.1667. Okay, so that's how problems involving dice would work if we encounter any of those. What I would like to do now is just describe some things that are true about probabilities and define a few terms for us. So now that we kind of have our feet wet and understand how probability works, one thing that you may have noticed is that for any event E, it must be the case that probability of E is between 0 and 1. It's not possible to have a negative probability, and it's also not possible to have a probability that's more than 1. This is probably easier to see if you look at the decimals, right? As we go through these problems, you'll notice that they were all between 0 and 1, right? All of our answers, they're always going to be between 0 and 1. And the reason for that is because if an event is impossible, right? If an event cannot occur, then there are 0 ways for it to happen. And so the probability of it occurring would be 0 out of however many possibilities there are in the sample space. But 0 divided by anything is just 0. And so this is the smallest that a probability can be. It doesn't make sense to say that there are -7 ways that something can happen, right? That's a nonsensical thing. On the other hand, if you know for a fact that the event will occur, then if you're counting up the number of ways that it can happen, it would have to be equal to the total number of possibilities because you're guaranteed that it happens, right? And so if you had something like, well, there are 27 ways that this can happen out of 27 possibilities, anything divided by itself is 1. And so that's the largest that a probability can ever be, is 1. I'm making a big deal out of this because if you are working on a probability and you get something that's negative, or if you get something that's more than 1, you know you've made a mistake somewhere and you've got to go back and fix it, okay? But probabilities are always going to be between 0 and 1. A general kind of rule of thumb with probabilities is that if we encounter a probability that's less than 5%, right? So if the probability that something occurring is less than 5%, or in other words, less than 0.05, we would call that an unusual event, okay? When we go to do inference in the third unit, we'll change this number depending on the situation, okay? But for now, kind of as a general rule of thumb, if there's less than a 5% chance of something occurring, then we would call that thing unusual. Another definition that we should go over is classical versus empirical probability. All right, the probabilities we've been computing so far are called classical probabilities. With classical probabilities, we know exactly what the sample space looks like, and so we can use this formula that we talked about on the previous page, or on the first page. But we don't always know what the sample space looks like, and I'll give you some examples of this. But sometimes it's just really complicated to know what the sample space looks like. And in that case, what we would have to do is just run some experiments. And based on our experimentation, based on the data that we have, we can use the relative frequencies in our data set, right, to approximate the probability, right? So approximate the probability of something happening, and that would be called empirical probability. I'm not going to make a huge deal about the distinction between those things, but let's take a look at some examples so that we can kind of see the difference. It is an important difference, and one that I'll point out at the end of the section. So number 5 here says, A fair six-sided die is rolled. What is the probability it lands on a 4? So we'll calculate that, and then it asks a follow-up question: is this classical or empirical probability, and is it unusual to roll a 4? Well, let's see, right? The probability that we roll a 4, well, on a standard six-sided die, there's only going to be one 4. So the probability of rolling a 4 is 1 out of 6, because there are 6 possibilities on a die. So 1 out of 6. We just changed this into a decimal on a different problem a second ago, but this is approximately 0.1667. Now the follow-up question: is this classical or empirical probability? And the answer is, well, it's classical probability, because we knew exactly what the sample space looked like, right? We knew that the die had 6 numbers on it: 1, 2, 3, 4, 5, and 6. And so we could use this formula, right, to calculate the probability. We just counted up the number of ways to roll a 4, which is 1, and divided by the total number of outcomes, which is 6. So this is classical probability. To answer the second follow-up question, is it unusual to roll a 4? Well, the probability of rolling a 4 is 0.1667, right? So this is 16.67%. And we said that something would be unusual if there's less than a 5% chance of it occurring. That's not the case here, right? So we say this is not unusual. Since probability of rolling a 4 is it's approximately 16.67%, which is more than 5%. Okay, next one. Number 6 here says, Pass the Pigs is a Milton Bradley game in which pigs are used as dice. Not real pigs, little plastic pigs. You throw little plastic pigs, and based on the way the pig lands, you get a different number of points. So points are earned based on the way the pig lands. There are 6 possible outcomes when a pig is tossed, but they're not equally likely to occur. Okay, so we have to rely on some experimentation here, I think, to figure out what's the likelihood that the pig is going to land in a certain way. In this case, we've got a class of 52 students who ran the experiments for us. They rolled the pigs 3,939 times. If only they had rolled it just 61 more times, they would have had a nice even 4,000. But alas, they did not. That's okay. The number of times each outcome occurred is recorded in this frequency table, right? So we've got a frequency table here. Part A says to use the results of this class's data collection to estimate the probability that the thrown pig will land on side with dot. And then as a follow-up question, is this classical or empirical probability? Okay. So the probability that the pig lands on side with dot is going to be the number of times that the pig landed on the side with dot, right? 1294 out of the total number of times the pigs were thrown, which was 3,939. And I have no idea if that reduces. I don't think it does. But we'll put it into decimals. 12,094 out of 3,939. It does not reduce. So that's the final answer. But as a decimal, it's approximately 0.3285. So there's about a 33% chance, right, that the pig is going to land on its side with the dot. By the way, maybe I should explain these outcomes, right? There are 2 sides that the pig could land on, and so they put a dot on one side to distinguish between them. So you've got side with dot, side without dot. Razorback is if the pig lands on its back with all four of its hooves up in the air. A trotter is when the pig lands on its feet. So that's got to be fairly infrequent, right? A snouter is even worse. A snouter is when the pig lands on its front two hooves and on its nose, and so it's balancing like a tripod on its front two hooves and its nose. And then finally, a leaning jowler is when the pig lands on one of its hooves and its nose, and it's just balancing on those two things. So that's got to be pretty unusual, right? Throwing a leaning jowler. I'm kind of giving away the next problem, I think, but okay. Getting back to the task at hand. So this is the probability of landing on the side of the pig landing on the side with the dot on it. We're asked, is this classical or empirical probability? And the answer is, this is empirical probability. This is empirical probability. Okay, because we're using the results of this experiment. A classical probability is something that you should be able to figure out just with like paper and pencil and your brain, right? An empirical probability is when you have to do some experimentation to figure out, what the likelihood is of an event occurring. And in this case, that's exactly what happened, right? We had a class of 52 students who ran an experiment. And so we're basing our probabilities on their experimentation. That makes this empirical probability. Would it be unusual to throw a leaning jowler? Well, we defined an unusual event as something that has less than a 5% chance of occurring, right? So let's see what the probability of throwing a leaning jowler is. It would be 32 out of 39, 3,939. So 32 out of 3,939. Which is approximately 0.0081. And that's definitely less than 5%, right? That's less than 5%. So yes, it would be unusual. To throw a leaning jowler. So probably that outcome gets more points in the game. I don't know. I've never played the game. But probably it gets more points because it's so unusual for you to throw a leaning jowler. It happens less than 1% of the time, right? It happens like 0.8% of the time. Okay. So let's talk about the relationship between classical probabilities and empirical probabilities. They're tied together with a fact called the law of large numbers. And what the law of large numbers says is that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer and closer to the probability of the outcome. In other words, the more experiments you do, the closer your empirical probabilities will be to your classical probabilities. And let me just show you, like with a thought experiment, why this would be true. Let's suppose that you flip a coin 100 times, okay? Now we know going into this that the classical probability of flipping heads is 1/2, right? There are two outcomes on a coin, heads or tails. One of them is heads, right? So probability of flipping heads is 1/2. But let's pretend that we compute the empirical probability of flipping heads after each flip of the coin. Okay, if we do that, let's say that the first flip is tails. If the first flip is tails, then we've only had one flip of the coin so far, and 0 of them ended up with heads, right? So the empirical probability of flipping heads after the first flip is 0 out of 1, which is 0. But now let's say that the next flip is heads, all right? So now we've had 2 flips of the coin, and one of them landed on heads, right? So the empirical probability flipping heads would be 1 head out of 2 flips. Okay, now let's say that the next flip is heads again. Now we've had 3 flips of the coin, and 2 of them landed on heads. So the empirical probability after the third flip is 2/3. And we could pretend that we've done this over and over and over again. But ultimately, in the long run, what we expect to happen is, so after the first flip, right, the empirical probability was 0. The empirical probability was 0. After the second flip, the empirical probability was 1/2. After the third flip, it was 2/3. And then maybe after the fourth flip, we get another tails and it's back down to 1/2, and then heads again, and heads, right? And so maybe the probability stays above 1/2 for a while, but eventually, right, over time, the empirical probability flipping heads is going to get closer and closer to 1/2, right? So this is what the law of large numbers is saying, right? Saying that the more experiments we do, the closer our empirical probabilities get to our classical probabilities. So that the law of large numbers justifies our use of empirical probabilities to approximate classical probabilities so long as the sample size is large enough, right? If you only had like a sample size of 5, then you wouldn't get a very good picture of what the true classical probability is, right? You would have, in this simulation, you would have an overestimate, right? But in the long run, right, if you had a sample size of 100, right, then you get a better picture, right? Your empirical probabilities will be matching your classical ones. Okay, one more topic in this section really quick is the complement rule. So the complement, let's say that S is your sample space, okay, as usual. And let's say that E is an outcome in your sample space. It's some event in your sample space. The complement of E is denoted by this E to the C power looking thing, but we read that E complement. Okay, and it's the set of all outcomes in the sample space that are not outcomes in the event E. So that's what we mean by complement. And note that it's complement with an E here, not complement with an I. In other words, it's a complement. It's a thing that completes another thing, not a compliment like an expression of praise. Okay? I think noting the words there, I think maybe helps to understand what they mean, right? A complement with an E is the thing that completes another thing. So a complement completes an event in the sense that when you put the event together with its complement, you recover the entire sample space. If I were to draw a picture of this, it would be like I could maybe represent the sample space with a box. So that's our sample space S. And maybe E is some event inside the box, right? And E complement would be everything else. All right? E complement is everything else in our sample space. Okay. If we need to compute a complement, we'll use the complement rule. We'll say probability of E complement is 1 minus the probability of E. And this makes sense. Maybe it makes more sense if you think about it in terms of percentages, right? But 1 is the same thing as 100%. So for E complement, it's going to be whatever the probability of E is. Let's say there's a 30% chance that E occurs. Then that would mean there's a 70% chance that E does not occur, right? 100% minus 30% is 70%, right? So that's what the complement rule is saying. For example, according to the American Veterinary Medical Association, 31.6% of American households own a dog. Part A asks, what is the probability that a randomly selected household owns a dog? Well, if 31.6% of households own a dog, then the probability that you're going to randomly select a household that owns a dog is going to be 0.316. Problems like that are like deceptively simple. It seems like there's got to be more to it than that, but there's not, right? It's just this is the probability of owning a dog, right? Part B asks, what's the probability that a randomly selected household does not own a dog? We could call that dog complement, right? These are going to be all the households that don't own a dog. And, well, that's going to be 1 minus 0.316. Oh, what is this? 0.684 maybe? 0.684. Let me double check. I sometimes struggle with subtraction. 0.316. Yeah, 0.684. So this is, that's how we would use the complement rule, okay? In other words, if 31.6% of people own a dog, then 68.4% of people do not own a dog. And that's all there is to that. That'll do it for this section, this brief introduction to probability, and I will check in with you again in the next one.